Okay, so I guess it's going to be a very small class today. Get started. It's a couple minutes early, but we can get started. So today we'll continue our discussion from last time on distributed file systems. Last time we did a case study of NFS, network file system, and today we will continue that discussion and we will talk about Coda, which is a very different file system, and then I'll talk about xFS, log structured file system, and then if we have time at the end, I'll briefly introduce HDFS and object storage system. Okay, but a couple slides from last time that from NFS that I couldn't cover. Let me finish those, then we'll start talking about Coda. So remember, NFS is a client-server file system. So files are stored on the server. Clients will actually access the files on the server using RPCs. Okay? So the question is, let's say the client is trying to read or write a file. It sends an RPC message, but maybe the message does not get delivered. It gets lost or something happens to the message. Then what should happen in this case? Right? So typically what will happen in an RPC system is the client will time out if it hasn't received a response from the server and resend the request. Okay, so you will see here it sent request number 1, 2, 3, 4. It basically didn't hear back in time, so it sent another request. Same request went again 1, 2, 3, 4. Okay? But from the server's perspective, if you're receiving the same RPC multiple times, if you execute them multiple times, let's say, then you have a problem because the RPC could be a write RPC saying append a character to the file. Okay? So it may be that the reply was lost, the RPC was received, but the reply didn't come. So it was successfully executed at the server. If the client times out and sends the same request again, then you are going to have an incorrect result where the same RPC has now appended that character or some data twice when it should have only done it once. Okay? So this goes back to the RPC failure discussion we had a while back when we were talking about distributed communication. And I said that RPC execution must be idempotent. Okay? Idempotent is just a term that says that no matter how many times you execute a certain operation, the results are the same. Right? So if you have that property in your system, it's called idempotency. Right? So we want to ensure that our RPC executions are idempotent. Right? So in this particular case, no matter how many times the client sends the same request, right, you should only the result at the server should be as if the RPC was executed exactly once. Right? So that's the property you want. So how do you implement idempotency? So in this case, what the server is going to do is it's going to keep a log, okay, or what is called a request response cache. The log is going to keep track of all recently executed requests, okay, and the responses they generate. So when a request comes in, RPC request comes in, the server, the NFS server will first look at the cache or the log saying, have I seen this request previously? Has it already been executed? Okay? If the request is present in the log and there is a valid response, you will just take it from the cache and return the result. So you will say, maybe the reply didn't reach the client, so let me just retransmit the reply. You won't execute it again. Okay? But if you don't see the request in the log or that cache, then you will say, I've never seen this request before. So this is a new request. It should be executed like normal. And you will execute it, process it, and put it in the cache. Right? So those are the scenarios that are actually shown here where you will see the scenario I mentioned where the request on the third figure where the response request is sent. Okay, it's processed, you put it in the cache, but the reply is lost. You send it again, you take it from the cache and you return it. Do not execute it again. Okay? So if you maintain this type of cache, you can implement idempotency in a fairly straightforward manner. Okay? So that's one way you can deal with RPC failure. An even simpler approach is to not use UDP as your transport protocol. You use TCP, in which case if the request or the response is lost, TCP takes care of that for you. You don't need to worry about it at an application level to keep this type of a cache. But if you are running your RPC on top of UDP for efficiency reasons, you will need techniques like this to be implemented. Okay? Yes, question?
After cache, other whatever process request we have, are they also, they have like a transaction number or something?
Yes. Yeah, so no, finish your question.
Suppose So we want to make sure that the server processes it
Yes.
correctly
Yes.
instead of just sending it.
Yes.
Okay,
Okay. So question is, what happens if you get two similar RPCs? How do you know that it's whether it's a duplicate or the same RPC retransmitted? You need to distinguish between those two cases. So the thing I did not explicitly mention is every RPC request needs to have a unique ID. Okay. So if you are sending two distinct RPC requests, they will have two different unique transaction IDs or RPC IDs. So you can track which RPC it is. So if they retransmit the RPC, it will go back to the server with the exact same number. But if there are two, let's say, write calls, each of them says append this character, the same character to the file, they are two independent requests. So you're not actually looking at the request itself, the RPC request, to figure out if it's a duplicate. You're looking at the RPC ID to check whether it's a duplicate. So that's how you're going to distinguish between duplicates and non-duplicates. Okay. Yes, your question. Okay, how do you ensure unique transaction IDs across clients? So if you just, so that's a good question, but there's a straightforward answer to it. So if you just have integers, okay, as IDs across clients, there's clear chance that the IDs might get duplicated, right? So you just have an integer that's incremented. You might have two clients have the same transaction IDs, then it's not unique. A more straightforward way to make it unique is clients have their own IDs. So you can have a client ID and an integer from that client. So for example, you might want a IP address, which is unique to a client, and then an integer appended to that IP address that gives you now a sequence number for that client, right? So you can disambiguate across clients by adding a unique client ID in addition to the RPC ID. That way you can distinguish. So that's a very straightforward way to do it. Of course, there could be other ways where you can take the integer space and say you get IDs X to Y. If it's a large enough integer space, maybe you don't need to worry about it, and some other client gets X plus 1 through something else. So you can do that, right? But you need a way to make sure they're unique, right? Okay, one more thing, and then we'll end NFS and start the new topic, which is going to be Coda. But I do want to mention that because client and the server are all talking over RPCs. Okay? RPCs, whether you use TCP or UDP, go over the network unencrypted, right? So whatever data you are sending from the client to the server, okay, is vulnerable to snooping by an adversary. So if you're trying to write to a file and you're sending the contents of the file are going as a write RPC from the client to the server, if there is anyone on the network that intercepts that packet, you will actually get to know what the contents of the file are that are being written. Okay, because it's unencrypted traffic. RPCs, none of the RPCs you have developed for any of your labs are encrypted, right? So if your client and the server are on the same enterprise network, maybe it's less of an issue. But if the client and the server are actually operating over the internet, your traffic is actually going unencrypted on internet, which is bad because someone can now figure out you're writing to something confidential to a file, and now someone can look at the contents of the traffic and figure out what is being written and so on. So that's not good. So what NFS version 4 onwards has started doing is they actually allow you to add security to the RPC layer. Okay? So you have something called a secure RPC, which encrypts all traffic before sending it, and then the server has to decrypt it, and vice versa. And this is important because it will then allow you to have NFS work over larger networks where you do not necessarily trust every entity in the network. They can then intercept your traffic, right? So encrypting your traffic operations is important. It's going to add overhead because encryption and decryption, which we will look at in 2 classes from now, okay, does add overhead to the operations, but it will provide security. Okay? So this is something you want to keep in mind. Okay, all right. So let's switch gears and talk about a different file system. This one is called Coda. Okay? This is an old file system. This is NFS was designed in the late 80s. This was designed in the, I would say, late 80s, early 90s as well. So it's almost 30 years old now. Doesn't really exist. It was a research project that never became commercial. Some parts of it were commercialized, but not this entire file system. This was a file system that was designed at CMU as a research project, but that very different goals from NFS, which was a client-server file system. So this is a distributed file system that was explicitly designed for mobile devices. Okay? So think about laptops or phones that are trying to access data from a server. Okay? Now, the main difference between mobile devices and maybe a desktop is mobile devices operate over a network where they can actually get disconnected from the network occasionally, right? So let's say you have a laptop, it's on a Wi-Fi network, it is now connected to the network. Okay? Maybe you shut down this laptop and go home, take a bus home. At that point, the laptop is not connected to the network, right? So, and then you might start working at your home and the laptop gets connected again. Okay? So this type of behavior is called disconnected operations, where or weakly connected devices that often have disconnections. Weakly connected essentially means that connectivity may come and go. It's not always assured, as opposed to a desktop that's connected on a wired network, which will largely be up at all times. Right? So now the question is, if you want to design your file system for a mobile world, what design decisions would you change? How would you make a decision different from, let's say, NFS? Okay? So what might we want to change? So that's the question that Coda asked, and there were several issues that we'll have to think about. Right? First is client disconnects from the network. Easy example is, let's say you take a flight, you go on an airplane. Right? So now even airplanes have Wi-Fi, but assume that you're on a plane with no Wi-Fi at all. Okay? You open your laptop, okay? Server is no longer available, right? Because you're disconnected from the server. And the question is, can you actually access any of your data? Typically, if in normal file system, you will not be able to access any server storage until you are back connected to a network. So clients, when they get disconnected, they may lose access to data. That's the first problem you got to deal with. Okay? Second problem you got to deal with is consistency. Remember, in NFS, we said the client might cache some data. If the data changes, the server can push invalidates to the client. Okay? But if you are disconnected from the network, consistency cannot be assured either. Right? So consistency becomes a problem if the client is not even connected. So when you design your systems for mobile devices, you got to think about these issues. Right? So here is how Coda is going to work. Okay? Coda allows you to have what is called a disconnected mode. Okay? So if you are now disconnected from the network for any reason, okay, Coda will allow you to continue to access your data as if nothing has happened, as if you're still connected. Right? The way it's going to do this is going to aggressively cache files, okay? So that when you disconnect, some subset of the files you typically access are already cached on your machine. And when you're trying to open your files, it will pretend like you're still connected, but serve data from the cache. Okay? Of course, if the caching algorithm does not cache some files that you try to open when you're disconnected, you're going to be out of luck. Okay? But if it makes some reasonable choices on what subset of the data from the server to cache, then you can be disconnected and essentially you will not have any problem. Okay? So this type of techniques now are also seen in cloud-based storage. For example, if you use Google application like Google Mail or things like that, they have an offline mode. Okay? You turn on offline mode in Google, you can still use a web browser and read your email because it will cache some of it locally, and it will not know that you're disconnected from the web, for example. Right? But this is the system that actually originated some of these ideas maybe more than 30 years ago. So let me explain how Coda works. So here is a diagram of how the client works. So think of a client that needs to now has access to a server. It can be in one of three states. Okay? It can be in a state called holding, it can be in reintegration, or it can be in emulation mode. Okay? So when you are connected to the server, okay, you are essentially going to be in holding mode. In holding mode, the client, the Coda client is going to start downloading files from the server that it wants to cache, okay, assuming the client will get disconnected at some point. Okay? So that's why you're trying to hold files before the disconnection event actually takes place. Now you can get disconnected at any point, and when you get disconnected, you go into emulation mode. Okay? When the client is in emulation mode, the Coda client will pretend as if it's still connected. Nothing would have changed. You open your machine, you open files, everything looks exactly as is, assuming the right files are hoarded. Right? So the client will not even see that there has been a disruption. You will continue to work as it. Right? So it will make the impact of network disconnection transparent to the user, so long as the hoarded data actually is the data they're trying to access. Okay? So maybe you're disconnected for a period of time, you go on a plane, you modify some files, and then eventually you are reconnected. Maybe you land and then you connect back to Wi-Fi. Then you go into reintegration mode. In reintegration mode, your client will actually talk to the server, and first it will upload all the files that have changed to the server, so that the server now has the updates, and the reverse as well. If some of the files that were hoarded have changed, okay, it will download them again, so that you have now uploaded your changes and you download all the new data. And once that is done, okay, reintegration is complete, and you'll go back to hoarding mode, saying, should I have downloaded some more files? Did the user try to access files that were not present on the machine while there was a disconnection? And you might hoard some more files or throw out files that have not been accessed for a long time, and then this pattern will repeat. Okay, so you can be in hoarding mode, where you can go prefetch content, okay, and cache them. You can be in emulation mode, where you are disconnected, but the mobile device does not actually make that disconnection visible to the user. It just looks like you are connected, you can access your files, nothing would have changed from the user's perspective. And then once you connect again, all your changes are synced to the server, and changes from the server are brought to the client. Is that clear at a very high level what Coda is trying to do? All right. So that's the basic operation in Coda. This is how you can allow your users to continue to access the data even if they're disconnected from the server. You could not do this in NFS, because NFS by default actually uses the server to perform all of its tasks. So if the server is you're disconnected from the server, all of the data that's stored on an NFS volume becomes unavailable until you reconnect. Okay, in Coda, that's not the case. Yeah. All right. So some more details about Coda before we talk about other issues that are relevant in this case. So here is kind of the thing you want to keep in mind. This is a distributed file system where you can have multiple servers. Each server can host some subset of the data. So here you will see that there are 2 file servers, okay, that are part of the Coda file system. Maybe some types of data are stored on this file server, some other types of data stored on another file server. There is a volume database that keeps track of what files and what directories are on what server. That's your metadata that you are going to check, because trying to figure out which files are on which server. Okay? And then so each file will belong to exactly 1 volume. Okay? The volumes can be replicated. So this does not show you any replication. It just shows you 2 file servers. So if you want, you can say this data can be now replicated across multiple servers. It supports that feature as well. That way, if one server fails, okay, your data is still available to clients on another server. Okay? So you can tolerate clients getting disconnected from servers. You can also tolerate servers getting disconnected or failing if you use replication. If you do not use the replication features, of course, if the server goes down, then whatever you hoarded on your machine continues to be accessible. But if you want to get new data or anything like that, you will not get it until the server comes back. But if you have replicated it, you will actually have that as well. Right? So you can distribute your files, okay, across machines, or partition them across machines, servers, that is, or you can also replicate them if you want additional fault tolerance properties in your system. Okay, that's how Coda is going to store your files. Now, this notion was not there in NFS. NFS has some basic replication capabilities, but by and large, you do not use it in that mode. In Coda, you do. Right? So you use these features. Okay? So here's an example of what happens if you have server replication and some server disappears. Right? So let's assume there are 3 servers in the system, as is shown in this figure, S1, S2, and S3, okay? And they're replicating the same volume. Right? So maybe there's a directory that's replicated on all 3. Right? And then you cut the network in the middle, as is shown here. Okay? So client A continues to access those files on servers 1 and 2. Client B can access that exact same set of files on server 3 because they were replicated on all 3 machines, right? So clients can continue to access the file, they can make changes and so on. Okay? And when the network disconnection goes away, okay, the servers have to synchronize the content. Servers have to say S1 and S2 will talk to S3 and say what files changed on S3. They'll bring them over and they will say push their updates over to S3 so that the files, the replicated directories are synchronized. Okay? But you might have a case where there is a write-write conflict. Okay? This client opened a file foo on this server, modified it, and this client A opened the same file foo on S1 and S2 and modified it as well. Okay? So now you have the same file was modified on both servers, and you cannot just override one of the changes. You have a write-write conflict where the same file was modified, something has to be done about it. Okay? So first thing is you got to detect that there is a conflict. Okay? And once you detect the conflict, then second thing is you have to resolve the conflict. Right? So these are two things you got to deal with. So the first question is, how is Coda going to resolve this? Not resolve, detect the conflict. So essentially, what Coda is going to do is keep track for every file. It will version the file. Okay? Every time you write to a file, it will increment the version number, so you know what version of the file you're talking. This is like updating the last modified timestamp, but you have an integer that's tracking every time the file is updated. A new version number is assigned to that file. Okay? So not only is it going to keep track of the version number of the local copy of the file, it will also track whether the writes that were made to that file on that server, let's say S1, have been sent to the other server. So in some sense, it will have a version vector that will track not only its version number, but whether the version was actually updated version was transmitted to others or not. Okay? This is somewhat like the vector clock timestamp, but it's not really vector clock. It is a vector that is getting incremented on every update, but you keep track of which subset of servers have been sent this change. Okay? So in that specific example that I was talking about, let's say you start with version 1 of file foo. So the version vector is going to be 111, which means all 3 servers before the disconnection have version 1 of the file. Everything is consistent at that point. Okay? And then this example, you have this broken network. There's a disconnection. So the network is partitioned into 2. Okay? Client A can continue to access the file on S1 and S2, and B can access it on S3. Client 1 will update the file, okay? And then the version vector on S1 and S2 is essentially going to become 2 to 1. Okay? The 2 of these servers are going to increment the version to 2, but they cannot send the update to S3, so they will assume the update was never sent, so the version vector will say 2 to 1. Okay? And the same thing will happen on the other partition where B will write to the file, S3 will increment its version vector, but it cannot send the changes, so its version vector will remain 112. Okay? Now, when the network is healed, that there is no longer a network disconnection, S1, S2, and S3 will try to reconcile the changes. Right? So they will say foo was changed. Okay? Then they'll say who has the newer version. Okay? The way you figure that out is through the version vector. If one version vector is strictly greater than the other version vector, you say that's the newer version of the file, you update it. Okay? But now you are going to compare 2 to 1 with 112 and say which vector is greater. Okay? And this is the same problem as you had in the vector timestamp. For a vector to be greater, all elements of that vector have to be greater than the other element, and at least one element has to be strictly greater. Okay? And you'll say 2 to 1 is not greater than 112, neither is 112 greater than 2 to 1. Some elements of the first vector are greater than the corresponding elements in the second vector, and vice versa. So that will signal to you that this is a conflict, that the file was changed on both subsets of servers, and now you have a conflict. Okay? So this is how you will actually figure out that there is a conflict. Okay? Once there is a conflict detected, the server will not be able to resolve the conflict at the file system level. You will just tell the user, okay, that there is a conflict. No different from if you use a source code control system like Git. If there are, you can essentially have 2 users update the same portion of source code, and you will have a conflict that has to be then manually resolved. Right? So you will do the same thing here. You will actually trigger manual reconciliation. So you will tell the user the file was changed. You can figure out which one is the later version, merge the changes, do whatever it is that needs to be done to get the file back and then say that the conflict is resolved. That will become the new version of the file. Okay, so you will see some of these ideas that are present in Git and other systems. They originated 30 years ago in a similar context, but it was more of a file system context. Okay, so you keep track of version numbers. You can track when there are conflicts. You can force manual reconciliation. Okay. Now, if the file had only changed on one partition, like this one, you would have 221 here, and the version number would be 111 here. And then 221 is a version vector that's strictly greater than 111. So you just overwrite S3. There's no problem, no conflict. Okay? But if they are changed on both partitions, you will identify the conflict and force the user to resolve it. Is this clear? Any questions here? All right. So the last thing I want to say is, in addition to tracking version vectors and so on, Coda also tried to give you database-like guarantees, transactional semantics. So you could open a file, okay, and then create a transaction-like session where you make a bunch of changes and then do the equivalent of committing the transaction. At that point, all of the updates that were made will get committed as one atomic operation, or if the transaction fails, it is as if the process didn't write to that file at all. All of the writes that were made in that transaction all get undone. Okay? So it gave you this transactional semantics, which allow you to serialize operations and things of that sort as well. Okay? These kinds of semantics are typically not given in file systems. Those are more database-like concepts, but Coda was a very early file system that gave you transactional semantics. And then almost 2 decades later, these transactional semantics were adopted in NTFS. So Windows file system, which is NTFS, also supports transactional semantics in certain cases. It's useful when your files are databases. Right? Typically, if you're opening a file just for reading and writing, you don't want the additional transactional overhead. But if your file is a database, then it's a good thing to have. You can actually implement your ACID properties in a much more straightforward manner if there's OS level support for some of these things. Is that clear? Any questions here? Okay, so now we'll talk about another interesting file system. This is also a research file system. Okay, this is called xFS. Okay, X, you will see lowercase x. That X is more like a cross, which says that this is no server. Okay, that is why they chose that name. So this is basically what's called a serverless file system. Okay, so unlike Coda and NFS, which had a client-server architecture, in xFS there is no server. You just have a set of clients. Okay, some of the storage space on some of the clients may be used to provide server-like functionality. Your files are completely spread out across all the clients. It's more like a peer-to-peer like environment, okay, but it's a real file system. It provides file system like abstractions, but there is no real server in this case. Any client can be a client. It can provide some of the functionality of the server. Because clients may not have a lot of disk space, you have to use the disk space on lots of clients as one big logical storage, and then put your files across all of them to give you a big storage subsystem that can store lots of files. If you just said client 5 is only going to store my files, that may not work because the amount of storage it might have is much lower. Okay? So essentially, the idea was to remove the bottlenecks. It's a research prototype that was developed, but their idea was if you have some number of servers, whether it's one or some small number, it will still look like all the storage is centralized on those small subset of servers. They might become a bottleneck. Okay? If there are lots of clients trying to read or write, the small number of servers will become a bottleneck. But if you have lots of clients in your system, each client has some storage, is connected to a good high-speed network, why not make use of the storage space and bandwidth that's available across all of the servers and remove the server bottleneck? That was their design goal. Okay? You'll see what all things they did to achieve that goal. So they said, let's get rid of the server. Any machine can act as a server, or multiple machines will collectively act as the server in this kind of system. Okay? This system was developed at Berkeley. The Coda one was at CMU. Okay? Both are actually very interesting systems in their own right. But I'll give you all of the interesting things they actually did in case of xFS. Okay? xFS actually uses two concepts that were designed in other previous contexts. Okay? First was it used this notion of disk arrays and striping. Okay? And I'll explain what disk arrays and striping is. And the second thing it used was something called a log structured organization. Okay? So log structured organization came out of a file system called log structured file system, LFS. Okay? They took that idea and they implemented it in xFS. Okay? RAID storage or disk arrays and striping came out of the storage world, where you had this notion of a redundant array of inexpensive disks, also called RAID, to build larger storage systems. And they took that idea and they implemented it in xFS as well. So to understand xFS, you now have to understand these two independent systems that they built on. So I'll explain what each of those does, and then we'll see how they come together in xFS. That clear? Okay. So let's start with RAID, redundant array of inexpensive disks. So let's keep xFS aside for now. I'm going to just describe what RAID is. It's independent of xFS. It can be used in many different things, and we'll see what that does. Then we'll see what LFS does, and then bring that two things together. Okay, so let's start with RAID. Okay, what does RAID mean? Okay, so to understand what RAID is, let me give you first an example. Let's take a server, a single server, file server that's at lots of disks. Not lots of disk space, but lots of independent disks. Let's say you put 20 disks in that server. Okay, rather than just your machine typically will have one disk, right? So think of a server that has 20 disks or 100 disks and so on. Okay? And the question we want to ask is, what is the reliability of the storage on this server? Okay, that's the question. So you to understand this, you should say, what's the reliability of a single disk? Okay, then we can ask, what's the reliability of n disks? Okay, so essentially, the reliability of a single disk tends to be 50 to 100,000 hours, which is several years. Okay, you take a single disk, the typical mean time to failure, which is called MTTF. Okay, that's typically the lifetime of that component or the disk before it fails, tends to be a few years. So what's that? On average, you buy a new disk, it will last for a few years. After a few years of usage, it may fail. Okay? That's true for computers as well. You buy a computer, it'll run for several years. After a while, things get old, something might die, and the machine might die. Right? So typically, electronic devices, storage, have a lifetime of a few years. Okay? Now, if you put 100 disks, okay, you no longer can assume just because each of those disks has a lifetime of a few years, your system lifetime is actually a few years. That's not the case, because components can fail independently. If you go back to my discussion of a distributed system, where I said if each component fails with probability p, what's the probability there's no failure? And I said it's 1 minus p to the power n. As n grows, I said the probability of a failure keeps approaching 1. Right? Same argument is true here. Even though these components are independent, each of them has lifetime of a few years. You put them together, you essentially get much lower lifetime. So if you have 70 disks, okay, and each disk has a 50,000 lifetime hours, the probability of this entire array not having a failure, it goes down to 700 hours. That you can see is a few weeks. Right? So if you put a lot of disks, maybe every few weeks, there's a chance a disk might fail. Okay? That's just elementary probability is what it gives you. So essentially, mean time to failure has dropped from 6 years to 1 month. Okay? So you cannot now say, I'll buy a server, I'll put 70 disks, I have lots of storage on my server, and then maybe in a month later, one disk failed. Okay? Now some of your data became unavailable. So what you will now need is to essentially make sure that disk failures can be automatically handled. Right? You don't want that disk failure to cause loss of data, because there's some data is stored on it. If the disk dies, then the data becomes unavailable. So you don't want that to happen. So then the question is, how are we going to organize our storage on this server, which has lots of disks, that will allow us to ensure higher availability or better reliability? Okay? Because components are now going to fail much more across the system more frequently than the lifetime of a single component. Okay? This is going to give us this notion of a disk array. Okay? So what is a disk array? Okay? So disk array basically says that I can take multiple disks, okay? I can combine their storage and make this and provide this abstraction of a single large logical disk to the rest of the system. And this is called, so I take an array of disks and make it look like one bigger disk. So I'm going to draw a picture here to show you. Right? So here is disk 1, disk 2, disk 3, disk 4. So if I just put 4 disks in my storage server, they'll just look like 4 independent disks. You can store files on disk 1 or disk 2 or disk 3 and so on. Okay? But if you turn this into a disk array, this will just look like, to the end user, it will just look like one big disk that has the total storage of all the independent disks. Okay? You can no longer pick where you put your data. You just put it on this logical disk, and the file system will, or in this case is the storage array controller, will decide where your data is going to go. Okay? So that's the notion of a disk array. Is that good so far? Okay. So that's the first concept. Second concept is, okay, now that we have the single logical disk abstraction, if the user wants to store their file, where should you put it? Which disk should you put it on? Right? If you didn't have a disk array, the user wants to store a file, they have to choose, right, which directory and which disk does it go. They're manually making that choice depending on which directories. Now we have kind of abstracted that away. We have this big logical disk. The user said, create a file foo. Okay? Then the question is, where should the system put that file? Nearest disk. Okay? All the disks are on the same machine, so they are equally near. But so we didn't put them. This is just a single server right now. When we get to xFS, we'll put them on different machines, but these are all on the same machine. So the machine is just looking like one big disk. Okay? You can put the storage, you can put the file on the disk with least load. Okay? A reasonable choice. You created the file, you put it on a disk that had the least load, but now after a while the load changed. Load is not going to be static, and turns out that now became the most heavily loaded disk. So you ended up making a bad choice because you don't know, because the load is low now, you created this file, it may stay on the server for months or years, that the load will remain low later. Loads will change over time. Any other thoughts? What can we do? Sorry? Yeah, how will you distribute it exactly?
If you pick at random every time you want to start out, then it will be stored in a random disk.
You can pick at random is what you're saying. So you could pick at random. Occasionally that's a good choice, but you might have because you are now storing things at random, you pick a disk I at random, you see that it has lots of files already on it, you don't have enough room to keep your file. Okay? Because you don't control the file size either. File size is not equal. Some files are big, some files are small. So you may get uneven use of storage, you may get uneven use of bandwidth. Right? So a better answer is we don't pick, we just put all the files, okay, distribute their content on all the disks. Okay? So what you will do, this is what will get us to what's called striping. To do striping, you will take a file, okay? You will chop it up into smaller chunks, which we'll call blocks, disk blocks. So maybe you'll take a file, you'll chop it up into 1 kilobyte disk block. Okay? You'll store the first block on the first file. You'll store the second block on the second file. Store the third block on the third file. Okay, you'll do this in round robin fashion. Okay? So that means that every file is now stored, okay, in pieces on all the disks. Okay? So first block, so you'll essentially, you can just do round robin striping, which is block I goes on disk I mod n. Right? So that's where you'll end up. Okay. So now the question is, what did the striping give us? Why did we do this? Okay. Or maybe going back to the discussion we just had, how did it overcome any of the problems that I was talking about, load, storage space, etc.?
Yes, I think that will ensure a uniform log to all the.
Okay, so first thing is, let's say you're trying to access the entire file. Okay, so the file has, let's say in this simple example, 4 blocks. Block 1 is on disk 1, block 2 on disk 2, and so on. Right? So you can now send a request to the logical disk saying read file foo. It has 4 blocks. Okay, one request will go to disk 1, and one request goes to 2, 3, and 4. So your requests have gotten evenly distributed. Okay? There is no imbalance in the system. Okay? But second, more important property is you are now getting parallelism, which you did not get before. You can read the file at the speed of all n disks. Okay? If you had a single disk that stored all 4 blocks, you would basically read them sequentially because disks are sequential. You can't read blocks concurrently. So now you got parallelism as well. Okay? You are sharing, it's like almost doing parallel processing because you stored and now you're retrieving in parallel. So you could balance your load, right? Because each file request, assuming you're reading more than one block, goes to multiple disks. Okay? You don't need to worry about, is this disk full? Can I put a big file? All disks are equally used because all files are getting distributed. You get parallelism as well. Right? So disk arrays will give you good properties. They don't need you to choose which disk to use, whether that disk which was least loaded at one time becomes more heavily loaded, whether it runs out of storage space. All those problems are gone. You got parallelism as well. Okay? So these are all benefits of striping. Okay? But now let me talk about some limitations of striping. Okay? Because I said when you have lots of disks, the chances of the system experiencing failure have gone up. Right? So let's say disk 2 has failed. Okay, so what's going to happen now? Okay, so now if disk 2 has failed, all the data on that disk is no longer available. Okay? Now, if you had stored individual files on independent disks like before, then the files that are completely stored on disk 1, disk 2, or disk 3 will stay accessible, but the files that were stored on disk 2 have disappeared. Okay? So only if you have used independent disks and a single disk fails, only some fraction of the files disappear. Okay? But we use striping. We put all the files on all the disks. Right? So now if a disk fails, all your files are impacted because 1/4 of your data is gone. Okay? So every file, okay, some blocks of that file have disappeared. Right? Which is much worse than if you had not used striping from an availability perspective. You got all of these benefits of striping, but you have a big problem, which is if there's any failure in the system, all of your data is at risk, not some fraction of the data that was only stored on that disk. Okay? So now what we need to do is we have a disk array, but we need to add redundancy to it so that if that disk goes down, you can still access its data. Okay? That is going to get us to this RAID acronym, which says redundant array of independent disks. This is an array of independent disks, but this is not redundant. We didn't keep any extra information. We just use striping. Okay? But when you add redundancy, we'll now get better properties. So question is, how will we design that redundancy? Is that clear so far? Okay. So by the way, if you don't use redundancy and use striping, this is called RAID level 0. Okay? RAID actually has numbers. That numbers tell you what degree of protection or what type of protection scheme is present. If you have no protection at all, no redundancy, that's called RAID 0. RAID 0 means it is an array. Okay? There's no redundancy. Okay? We will talk about what RAID 1 and others do in just a second. Okay? So what is the first thing you can think of if you want to deal with failures? If some disk fails, how will you make sure the data continues to be available? Yes. Okay, you can replicate. Okay? So in the RAID world, this is called mirroring. Okay? I took that 4-disk example. Okay? And then for every disk, now there's going to be a backup disk. So there are now your 4-disk system will look like a 2-disk system from a storage perspective because the other 2 disks are backing up the previous disk. Okay? So what that means, every time you do a write, that write has to go to the disk. If that's a write of a block, that has to go to the primary and the secondary. Okay? So that because these are mirrored. Mirror means they're identical copies of one another. When you read, you can read from either one because the same data is present on both. Okay? So this is essentially called RAID level 1. It's called mirroring. Okay? So it allows you now to tolerate disk failures. Like essentially, in the previous case, if that disk failed, there is a mirror available, so none of your data is lost. Right? So you can continue to access it by accessing the backup disk. It has all of the data that was present on the primary disk that failed. Okay? So essentially, each write is become 2 physical writes because every write has to go to the primary disk and the backup disk. Okay? If you write to the entire array, you have to write to all of the backup disks as well. Okay? Reads can be optimized because reads can go to either the primary or the backup because both of them have the same data. Okay? But it's an expensive solution. Okay, you basically double the cost of your storage system. You want 1 terabyte of storage, you got to buy 2 terabytes of disk because you got to have a backup disk for every primary disk. Okay, so it's 100% overhead in constructing this system. Okay, so it's a simple solution, but you doubled your cost, and we want to see if there is a less costly solution available. Is that clear what we just said? Okay, so that's RAID 1. We'll now come up with a better approach, which is called RAID 2. Okay, sorry, not RAID 2. We'll start with RAID 4, and then we'll look at RAID 5. Okay, so here is another approach. Okay, rather than using mirroring, we can keep some redundant information, but that redundant information will protect the data on multiple disks, not just one. In mirroring, each block protects one block on the primary. So it's basically 2x is the cost. Okay? But we can do something better, which is try to protect maybe more than one block. And this is going to get us to this notion of what is called a parity block. Okay? So here's a 5-disk system. Okay? The black disks are data disks. The green disk is essentially a disk that stores extra information. It's just as we had a mirrored image, that's an extra disk. So in this case, the cost of extra storage is 1/5. Because for 4 disks, you added 1 extra disk to store redundant information. Okay? So we went from 50% to 20%, which is better. But the question is, how are we going to make sure that keeping that 1 disk around can allow you to tolerate the failure of any of the black disks? Okay? This is where we are going to use some simple XOR operations to understand how this is going to work. So here is how you do it. Okay? So you're still going to use striping. So here we have, you'll see D0, D1, D2, D3, D4. So those are blocks of a 5. Okay? So if you want to store the first 4 blocks, you'll store D0 here, D1 on the next one, D2, D3. Then you'll XOR those blocks. Okay? You will use the XOR operation on all of those blocks, and the resulting data is called the parity block, and you are going to store it here on the green disk. Okay? And our claim is going to be, if any of D0, D1, D2, or D3 become unavailable, we can use the parity block to reconstruct that block. The parity block is not a mirror of that information, but you can reconstruct it with parity. Okay? The question is, how do we do it? So let me give you an example. Okay, so I presume you at least know what XOR is, right? So XOR operation. So here is essentially A XOR B. Okay? You take 2 bits A and B, 2 variables with 1 bit each, A XOR B, and it gives you C. Okay? The XOR operation tells you, okay, if you look at the XOR table, if you say that if you have C and B, you can get back A. So if you do C XOR A, this is going to give you back B. Or if you have C XOR B, it is going to give you back A. Okay? This is a property of XOR. If you just look at the XOR table and you do this, you will convince yourself this works. Okay? You can now do this for more than 2. You can do it for 3. It's the same thing. Is that clear, first of all? You need to explain that, or is that clear? So that's the property of XOR. Okay? So now what that means is, let's say D0 becomes unavailable. That disk has failed. The first disk here has failed. Okay? The way you are going to reconstruct D0 is you are going to read D1, D2, D3, and the parity block. You are going to XOR all of them. It will give you D2. Okay? In this simple example, if the disk that stores A goes away, okay, you have to then read the block B, you have to read C, and then you have to do XOR over them. That allows you to reconstruct, or you have to do XOR over them. That gets you back A. Okay? You will do that exact same thing. Whenever any of these blocks become unavailable, you read the entire group. Okay? Minus that block, you XOR that group, you get back that block that disappeared. Is that clear, what I just said? Okay? So this is called RAID 4. Okay? So you keep a parity disk that is going to protect a set of disks. Okay? You have a question? Okay. If 2 blocks fail, the question is what happens if 2 blocks fail? So all of the RAID schemes I'm going to talk about today are designed to tolerate 1 disk failure per parity group. Okay? So 2 disks fail, then you cannot get your data. That's like just as if you had no redundancy, 1 disk failed, some data loss, you will have data loss. Okay? But you can design, there are higher levels of RAID that allow you to tolerate 2 disk failures, which we will not talk about. I'm just going to stop at RAID 5 today, and we'll end there. But yes, you can have other schemes. Okay, these are all coding theory schemes, by the way. You are using simple parity is the simplest form of code where you have redundant information. Your question, yes.
So this is RAID 4. What's special about having 4, D0 through D3? Couldn't this just be extended to arbitrary large number of data disks and then one parity?
Yes. The first question is you had one, is why only 4? Can this be extended to any number? So when you design, you configure an RAID array, you have to configure the size of the parity group, which can be arbitrary. You can have 10 disks and one parity disk. That one parity disk will protect those 10 disks. Okay? So you can design how you want to protect them. Okay? And there will be some implications, as we will see in just a second, of if you have large parity group, there's an impact on the parity disk. So you might not want to have gigantic groups where maybe 100 disks are backed up with a single parity group, okay? Because it will have an implication. Okay? But let's now ask the question how reads and writes are going to work in a parity in disk, in RAID 4. Okay? Let's first assume, okay, the simplest case is you write a large file, okay, which means that in this case, let's for sake of example assume the file has only 4 blocks, D0, D1, D2, D3. Okay, we'll ignore the latest 4 blocks. So the file is a 4-block file. Okay? You update the file, you write the whole file out. Okay? So in this case, as far as the file system is concerned, what it will do is it will take the 4 blocks, it will do an XOR. Okay? It will compute the P block, and then it will write 5 blocks out. It will write D0 to first disk, D1 to second disk, D2, D3, and the parity block. Okay? And you're done. Okay? So this is the large write case. In the large write case, you take the blocks, okay, because large write means it's a big write with lots of data you're trying to write at once. You take the blocks, you compute an XOR, okay, and you write the parity and the blocks, you're done. Okay. Now let's take the small write case. Let's say you open the file, you write 1 character to the file. It's a large file, you write 1 character and you save it. Okay. Maybe only D0 changed in this case. Okay. So what do we need to do to update everything? Okay, you got to recompute the parity. Okay, because the XOR will change the parity if any of the data has changed. Okay, so how do we do that? Okay, so first thing to update the parity is you need all of the blocks. That's how, because you're doing XOR over them. Okay, so you are going to read D0, D1, D2, D3, and the parity block. You'll read all of those. Then you will update the D0 block with whatever change you made. Okay, you will do an XOR. Okay, that will change the parity block, and then you'll write D0 and the parity block back, because those are the only things that change. D1, D2, D3 didn't change in this case. Is that clear what I just said? So small write will require you to read the entire parity group, which is all the data blocks and the parity blocks, into memory. Then you make a change to the block that changed. You will recompute the parity by doing an XOR and then write 2 blocks out. Okay? So n blocks are read. Okay? Recompute the parity, 2 blocks are written. Okay? So small write involves, okay, n plus 2 operations. N block reads and 2 block writes, even though you change the small block, small amount of data. Okay? So small writes are very expensive in this case. Okay? This is called a read, modify, write cycle. Okay? So you read, you modify the block you change, and you write out the data and the parity block. Okay? So in RAID 4, small writes are expensive. Large writes is no problem. You don't have to read anything. If they are overwriting it, you just compute the parity and just overwrite the blocks, write the parity block. So you have 1 extra write if you are writing the entire parity block. Okay? But if you are reading or writing 1 block, you have higher overhead. Yes.
Can we not just read the old whatever data we had at D0 and then compute what we have using the parity that we have D1, D2, D1 XOR D2 XOR D3? Then we again do the parity of the new D0.
Okay. So your question is, can you read D0 and the parity? Okay. You XOR them, you will get this middle. Okay. And then you can update these 2, and you can do that too. But still you got to read. So that's an optimization that you just suggested, which still requires you to read data, XOR, and write back data. Whatever it is, you have a read, modify, write cycle. Whether you read the remaining data and XOR it, or whether you read D2 and P and you XOR it, that gives you the combination of these three, is fine. That's a good observation, but still there is a high overhead. Okay? If this was normal file system, one write is just one write to the block. You're not reading anything and writing. Here there is additional overhead. That's the main point you want to make. Okay, so that's a problem. So we can't solve that problem with parity, but it's a problem you want to keep it. But here's the other question, right? So let's say you are trying to now write to different disks. Okay, so maybe you are updating the first disk and the third disk and so on. Any write operation will always touch the parity disk as well, because every write will update the parity block. Okay? So if the first disk gets maybe 1/n of the writes of the entire system, second disk gets 1/n, this disk is going to get the sum of all the writes. Its load will be n times bigger than the load on all the remaining disks, because any write on any of this will fundamentally also update the parity block. So the parity disk will get all of the load of all the remaining disks as well when you're doing writes. Not reads, but when you're doing writes. Okay? So in other words, the parity disk is going to quickly get overloaded if you have a write-intensive system. Is that clear, what I just said? Okay? Because whenever you write, you have to essentially update the parity block. That should be clear, because if you update any block, the parity changes. So what that means is any update to any of the disks also causes a write to the parity disk. And so the parity disk sees the load that's the sum of the write loads on all the other disks. Okay, so what can we do in this case? Okay, so this will cause a system overload, right? So we don't want that disk to be overloaded. Yes. Yeah. Can you repeat what you said? If you're yes. Yeah. The question is, if you write to all the blocks in the parity group, then the parity needs to be updated only once. I'm just talking about different applications writing to different parts of the disk, not that your same application writing to one file. There are many files on this disk. They're all been striped. Application 1 writes to one block of file 1. Application 2 writes to another block of file 2. Application 3 writes to some other block. This parity disk will see the load on all caused by all of those. That's what I'm trying to say. Not that one application wrote to the entire parity group, in which case you're right. That is true. But in any case, here is what I was talking about there. So if in RAID 4, if you have D1 to D3, you do an XOR, you get the parity. Any disk fails, you can replace reconstruct that data by taking all the remaining data and XOR. Okay, but all parity blocks are stored on the same disk, so parity block will become a bottleneck. What are we going to do now? Okay, so one suggestion is don't update the parity every time. Okay, every once in a while you go and construct the parity and write it. Okay, you will get better performance, but you are putting the system at higher risk, because if you did not update the parity as soon as the write happened and the disk failed, that file is actually now corrupt because you don't have the parity to reconstruct. Any other data that was not changed is still fine. Right? So yes, you can trade performance and reliability. That's a trade-off you can make. There are other things you could do. Yes. Yeah, so that was the same suggestion. If you make it you can make it asynchronous. Okay, that might reduce the load, or you can batch the writes and so on. But you will lose reliability because you're holding off on updating the parity. In the meantime, if there's a disk failure, you don't have the parity to reconstruct whatever data was written before the asynchronous update of parity. Right? So yes, you will have that problem. Okay? But you could distribute the parity. Why should we put the parity on one disk? Right? You could say for the first parity group, disk 5 stores the parity block. For the second one, I put it on disk 4 and so on. Right? So rather than having one dedicated disk, I distribute the parity, not the priority. Okay? So this will mean that all the disks now share the load of the priority updates rather than only one disk getting it. And now you have a more balanced system. Okay? You still have to update the parity disk. You still have to do the read, modify, write. Okay? But at least the load is more evenly distributed where you don't have a single disk becoming the bottleneck. Okay? So if you use RAID 4, but then remove a dedicated parity disk and distribute it, you end up with RAID 5, okay? Which is still by and large used in many storage systems. The default protection level, if you buy a disk array, is recommended to be at least RAID 5. You can then add higher level RAIDs to tolerate multiple disk failures, but RAID 5 is minimally recommended. Okay? So yes, the problem of small writes is not gone. If you have parity, you will still have that problem of small writes, and you can't change that. But at least we solved the imbalance problem. Right? Large writes, there are no issues. Small writes in RAID 5, RAID 4, you have that problem. Okay, even RAID 3, but we didn't talk about RAID 3. Okay? All right. So this is RAID. Okay? This is just background for xFS. We haven't gotten to how xFS uses this, but at least now you know large storage systems, they will have multiple disks. Okay? They will have hardware controllers because XOR is going to be computationally intensive. So if you have high write based applications, you will actually have a disk controller that is implementing XOR in hardware. So you can do this much more efficiently rather than writing code where you read it. You actually do this XOR in memory and write it back. You can do this in hardware to improve performance and so on. But still, we have all the issues of small disk writes and whatnot. Okay? So we'll keep this in mind. Okay? So xFS is going to essentially use not hardware RAID, unfortunately. We'll use software RAID because the disks are not on one machine. Okay? Remember, I said it's a serverless file system. You have a set of n machines. All of them act as a part of a storage server. So first thing is you're going to take your files and you're going to stripe them across all the clients. Okay? So essentially, you will do what we did in RAID, but you will put disk block 1 on the disk of machine 1 and block 2 on the disk of machine 2. So they will be on different machines. In RAID, all the disks are on a single machine. Okay? Here, you now distributed it across, same concept, except that you're striping over a network, not striping over disks on the same machine. Okay? So you will essentially, then you have to use software RAID because some machine has to compute the parity. There's no controller on the one machine to do it, but you will essentially do striping across machines. You will use software RAID to update parity, but everything else is the same. Right? So now you have used the storage space on lots of clients and make it look like one big logical disk as far as xFS is concerned. So it's aggregating the storage space on multiple machines and making it look like one big storage system. So, and these machines are, none of them is a server. They're all like peers. They can be client or a server. Is that clear? Okay. So that's the first concept. Second concept, log structured file system. And that's also part of xFS. So let me explain what log structured organization is, why it matters, and so on. Okay. So this was a completely different file system that was also designed in the 80s, in early 90s, and xFS actually took that idea and implemented it. Okay. So we need to understand what log structured organization is. Okay, and then we will try to understand what this is. So the log structured file system was designed with one specific goal, which was if you have a storage file server with a big memory cache, okay, how are you going to optimize the design of the file system? Okay, and the reason, and you'll see why the cache actually makes a difference. Okay, so think about a standard server. Okay, the data is stored on disk. Okay, disks are slow. Okay, always the disks are slow. So you always put a cache in a file system, any file system. You will have a memory cache where recently accessed data is in the cache. If there's another request for that same file or the same block, you serve it from the cache. You don't go back to disk. This will always speed up performance. So you always will have caching in any file system, in any operating system to speed up disk access. Okay? Now consider a case where you put a big cache because you have lots of RAM. Let's say you put 1 GB of your 10 GB or whatever, 15, 16 GB for an OS cache. Okay? So what is now going to happen is every time there is a read request that came into the server, okay, you'll first look at the cache. If your cache hit, you're done. You just return the result. If it's a cache miss, you go to the disk, you'll read the data, you'll put it in the cache, and you'll return it. So maybe next time you access the same data, now it's already in the cache. Okay? So over time, you will take the data that was most recently accessed, okay, and you will put it in the cache. Okay? So your cache hit will keep increasing because you have, if your traffic pattern has locality of reference, which means more recently accessed data has a higher chance of getting accessed again, you will have higher cache hits. Right? So now consider in this example where you have a system with a cache, and I'm going to make a small picture here. So this is your disk. Okay? This is the server. This is the cache. Okay? So this is essentially requests come in. Whenever there's a cache miss, you go to the disk. If it's a cache hit, you are essentially going to return. So the number of requests that are hitting the disk are strictly smaller than the number of requests that are coming into the system. So some of them are being absorbed by the cache. Okay? So let's assume in this file server, the number of reads and writes are equal. 50% of accesses are reads, 50% of accesses are writes. That's what is coming into your file server. Okay? Some of this data is absorbed by the cache. What do you think will be what the traffic will look like as far as the disk traffic is concerned? It will definitely be lesser because you're going to absorb the cache. But in what sense will it be lesser? So let's ask the question, what happens in case of a write and what happens in case of a read? Okay? Write request comes in. Okay? Even if it's a cache hit, that the data was already cached, you'll update the cache and return, but that data has to be still returned to disk. Okay? Otherwise, if the machine fails, you never wrote that data to disk, your data would have disappeared. So every write request will eventually trickle to it. It will immediately trickle or it will eventually trickle to the disk. Okay? And this depends on the type of caching. Okay? This is called write through or write back. Write through caching essentially means if the write request comes in, update the cache, immediately update the disk. It's called write through. The writes are flowing right through the cache to the disk. Write back caching says write to the cache, and then the request goes back, and later on you are going to write to the disk, but you will still write to the disk. Okay? But in both cases, you got to update the file eventually. Otherwise, you will not have persistent data. Right? So what this is saying is every write, okay, will eventually trickle to the disk. Okay, what about reads? Okay, the only disks reads that are seen by the disk are the misses. Okay? If you have a high cache hit rate, right, most of the reads are being served by the cache, only a small fraction of them are trickling to the disk. Okay? So even if you have 50% reads and 50% writes coming in, as far as the disk traffic is concerned, it will be predominantly writes and only a small fraction of reads. Okay? So your disk traffic is looking largely write traffic, and occasionally there are reads for the misses that are then going to be served from the cache after this point. Okay? So what this is saying is you should now optimize your file system for a predominantly write-oriented traffic, because that's the traffic the disk is seeing. Okay? If you assume that the disk traffic is equal reads and equal writes, and you optimize it for both reads and writes, you misoptimize it because that's not what the disk traffic is looking like. That's what the server traffic might look like, but not the disk traffic. So in a world where you use a lot of caching, the disks are seeing a lot more writes than reads. So then the question is, how are you going to optimize your file system for a predominantly write-only traffic? Right? So this is where we get to this notion of a log. Okay? So what the log structured file system says is typically when you write to a file, different writes are going to go to different parts of the disk, right? Because what the file system will do is when a write comes in, it'll say what block is available on my disk, and then if you see some block that's not being used, you will put that data there. And then the next write comes, you will say what block is available, and that write might go to some other part of the disk. So typically writes go to random locations on disk. Okay? But if you have write-only traffic, what you're going to do is you're going to write sequentially to disk. Okay? You will basically start at the beginning. Write comes in, you will write the first block at block 1, second at block 2, block 3, and so on. So this is why it's called a log. You're just writing it sequentially like a log. Okay? And the reason that optimizes your performance is when you have magnetic disk, like old style disk, not SSDs that you have now in your laptops, those disks are spinning disks. They're like a CD that's spinning. And then when you're trying to write at different location, your disk head has to go back and forth trying to write because it's mechanical. Right? So there's some overhead in moving the disk back and forth to write to the correct location. That's expensive. So rather than doing that, write sequentially. The disk head is just always writing to the next location, so that's most effective. Right? So in the old magnetic disk case, sequential writes give you the maximum performance because there is no disk seek overhead at all. Right? So you are optimizing performance by writing it sequentially. No question, yes. Okay, question is why would that not be the default behavior? So if you write as a log, there are some issues. Let's say you wrote to a file, okay, and you wrote that block to wrote that data to block 5. Now you open the file and you update it. In a normal file system, that write will go back to block 5, which is what you updated. Okay, but in a log structured file system, because you're writing as a log, this block will be returned to the end of the log. Okay, and then you have to mark that previously written block as deleted because you just have a sequential log and you're just writing to you're basically written this for, you're writing the next data here. So if that data is updating some data that was written previously in the log, that data is now going to be marked as deleted. Okay, so you created a hole in your log. Okay, over time, your log will get fragmented because you always write new data to the end, but that data is overwriting something that was previously written. So you are marking some middle parts of your log as being overwritten. Right? So you will, if you have lots of fragmentation, then you are back to the same problem. When you go to the end of the disk and you cycle back, okay, you will then only be able to write to the parts that were deleted. And then you are going to, because that's not sequential anymore, you will start writing to random locations. So all your advantages have disappeared. Is that clear? What I just said? Because you wrote to the log, and as you write each new block, your rule is I append to the, I don't go and overwrite. In a normal file system, you update a block, you go overwrite the block where it was previously stored. You don't go and create a new location and put it elsewhere. Here, every time you update, you create a new location for your data. Okay? So you are always appending to the end, but you are creating holes because you are updating blocks that are already written. So you have empty space here, empty space here. You cycle back to the beginning. Some parts of the disks have been written, some parts are available. So now you will write to one hole and then you'll jump to the next hole. You can't write sequentially. The advantages disappeared. Okay? So what will we do in this case? Is that clear? There are some problems with this approach. It looks good, but then you have a problem. Okay? So you have to run garbage collection. Okay? What garbage collection is going to do is it will defragment the disk. It will read all of that. It will compact it and put all the unused space at the end. Right? So now you have created extra overhead. Even though there are no reads and writes, you got to periodically garbage collect by reading all of the block, compacting it, writing it as a chunk, freeing up space. So I have big segments that are free that I can write sequentially as a log. So there is extra overhead in the system where you have to garbage collect. Okay? That overhead does not exist in any other file system. You don't actually do any garbage collection or defragmentation by default because you can write to random location. So long as there is free space, you can write anywhere. But in this case, we cannot write anywhere. We want to write sequentially. You want sequential chunks that are free. Right? So you got to defragment every once in a while. That introduces overhead. Right? So this is why log structured file system, they're a very good idea because of these problems of having holes in the middle that you have to defragment. Okay? They never actually took off. Okay? But it's a good idea. You can just write as a log and it's optimized for write performance. So long as you're willing to pay garbage collection overhead, still a good idea. But you don't want user to say my disk is creaking. It's saying I'm not doing any writes, but look at the amount of traffic because it just seems to be doing lots of reads and writes because it just started garbage collection. Everything slows down. Right? So you don't want that as a user experience. So it never really took off. It was a good idea. Okay? But coming back to xFS, okay, it decided because now you're striping across machines, we will essentially use log structured organization. In particular, we will actually write parity groups. We will essentially write a parity group as a log. We will compute the parity, write it. But then within each disk, you'll create logs. So you're writing sequentially across disks. You are going to, these disks are on different machines, by the way. They're not on the same machines. You are going to compute this parity. But then the next one will be sequential, return to the end of 2 and so on. So you're constructing logs on each disk that allow you to do sequential writing. you are getting parallelism across disks and so on. So it is combining log structured organization with RAID, right? So you will think of your entire disk as one giant log, right? Always appending to the end of the log, and that's basically allowing you to strike. Okay? And then within each, you are essentially also appending to the next location on that disk and so on. Okay? So you're getting right throughput on each of the disks. You're getting parallelism across this. So you're trying to combine some of these advantages. Is that clear? Any questions here? So that's going to bring us to the end of xFS. We've talked about log structured organization, RAID, and then the fact that this is a serverless, you put it all together, you get xFS. Yes, question.
Suppose we have fragmented we have to round robin, we append say one, but we need to remove something. That we have updated, right? Yes, one on P. On the new space that we have because we are doing round robin is one. So we still need to delete from the P and afterwards.
Yeah, so first thing is I didn't fully understand your example, but you still need to do garbage collection here. Okay? If block 1 gets updated, it will get written to the end of the log and it will get written somewhere else. Okay? And this block will be marked as deleted. The parity, you actually don't delete anything, just mark it as deleted in some other data structure. These other blocks have valid data, the parity is valid. So if some disk goes down, you can still reconstruct because you didn't overwrite this data yet. Right? But you just mark somewhere saying block 1 has been deleted. Eventually, when you do garbage collection, you will read all of this information, you will compact it. Some other data will have valid data will get written here, and then you will reconstruct the parity and write it out. Right? So you are never going to have that example that I think you are mentioning where if one block of a parity group gets deleted, I have to move something else because you are not actually, you're only marking it as deleted in a data structure. But the old data is still there, so the parity is still valid for failure recovery purpose. Only when you do defragmentation and garbage collection will you redo all of that. So it will have a lot of background overhead while you read, reconstruct the parity, compact, write it out, and so on. Okay? Yes. Okay. Question is in RAID 5, if one disk has failed, how do you know where the parts of the files are stored? That's your question, right? Okay. So as far as RAID is concerned, it's operating below the file system. It doesn't know anything about file. It knows only things about blocks. Okay? RAID and disks operate at a block level. They only know block 1, block 2. So all you know is there's a block number 1, block number 2, block number 3. You XOR them, I got a parity block, which is stored in as block 4. This is all that the RAID understands. The file system operates on top of RAID, where it keeps track of which files are mapped to which blocks of the file. So the simple answer to your question is the file system has metadata, which is your inode, which is an additional data structure that says block 1 of the file is on this disk, and that block 2 is stored here, and so on. So the file system will have to read its metadata to know where the data blocks are stored. Right? That's not understood by RAID. RAID does not know anything about files. RAID is operating at a block level, which is one level below the file system. Right? It only knows block. The file system layers a file abstraction on top of its block, and to do that, you have to keep track of the file data and the file metadata. Okay? Okay, question is if the parity block is not available. So let's say one disk failed. Okay, that parity block in this example, block 4 is gone, and some other data are gone. Other parity blocks are still valid for other parity. So what will happen is for this parity group, that parity block has disappeared, but the data is still there. For the next parity group, the parity will be on disk 3. So one data block has disappeared, but the parity is there. So to read that parity group, you have to read the rest of the data XOR. Right? So you will actually decide based on what is stored where, which disk has failed, how to do this. Okay. All right. So